identifying significant results with the range rule of thumb. The range rule of thumb for identifying significant values, here's our mu, and we have to know our standard deviation. If I say mu plus 2 times our standard deviation, whatever that number is, if it's that number or above, it's significantly high. And if it's mu minus 2 times the standard deviation, then if it's that number or below, it's significantly low. And anything else between those two values are not significant. What I mean by not significant is that they're not out of the ordinary. Identifying significant results. We found that when tossing 2 coins, the mean number of heads is 1, and the standard deviation is 0.7. And we want to use those results and the range rule of thumb to determine whether 2 heads is a significantly high number of heads. But I can draw, here's my mu, which equals 1. Then I have mu plus 1 standard deviation is equal to 1.7. And mu plus 2 standard deviations is 1 plus 2 times 0.7. This is equal to 2.4. And anything 2.4 or above would be considered significantly high. If you flip 2 coins and you get more than 2 heads, that would be pretty amazing. I would definitely say it was significantly high. And I'll do it in red. I can also go this way and I can say mu minus 1 standard deviation is 1 minus 0.7. So that's 0.3. And mu minus 2 standard deviations is equal to 1 minus 2 times 0.7. 2 times 0.7 is 1.4. 1 minus 1.4 is a negative value, negative 0.4. Use the results and the range rule of thumb to determine whether 2 heads is significantly high. If this is 1.7, this is 2.4, let's say 2 is right here. Well, it's not significantly high and it's not significantly low. It's just right in the range of no significance. Example, identifying significant results within the range rule of thumb. Based on these results, we concluded 2 heads is not a significantly high number of heads because 2 is not greater than or equal to 2.4, which is exactly what we said. Identify significant results with probabilities. Significantly high number of successes, X successes among N trials is a significantly high number of successes if the probability of X or more successes is 0.05 less. Why do we need that? Because we also have these continuous functions that we really can't count. This is our magic number. If the probability of whatever we're looking for or more is less than or equal to 0.05, it's significantly high. That would be more like that graph where we talked about the height. And this is the mean. And we have our bell curve. If the probability, which is the area under the curve, let's say that probability that I just colored in is 0.05. This is our X, and we're saying the probability of X or more. If it's in this yellow, then it's 0.05, or it could be less if it's further over. And the same thing is true over on significantly low. So let's say this is our point of X. This would be x plus 2 times the standard deviation. Anything lower would be the area under the curve to the left of that line, and that would have to also be p of x, x or fewer, is the probability is less than 0.05, okay? Or that area is that small. And this is kind of important. The value 0.05 is not absolutely rigid. Sometimes we could use 0.01 because maybe we want them to be even more significant, right? So it's not rigid, but that's the number we're mostly going to use. The rare event rule for inferential statistics. If under a given assumption, the probability of a particular outcome is very small, when we do our experiment, the probability of each outcome is very small, and it's so small that it occurs significantly less than or significantly more than the upper 5% or the lower 5% than what we expected it to be, then our assumption is probably not correct. And now we have something called the expected value. The expected value of a discrete random variable is equal to the mean. Expected value, mean, same thing. We can therefore find the expected value by multiplying our x times our probability that our x occurred for each event, and then we add them together, which is what we did when we found mu. Let's do an example. We draw a table, the probability of losing, winning, and here's my x, and here's my p of x, and my expected value is the same as the mean, x times p of x. If you bet $5 on the number 7 in roulette, the probability of losing $5 is 37 out of 38. If we lose, our probability is 37 out of 38, and we would lose $5. And if we multiply those two numbers together, we get negative 4.864. Now, if we win, so we bet $5, and the probability of making a net gain of $175 is 1 out of 38. We could get 175 times 1 out of 38. And that's 4.6052. Let's add those up. My expected value is going to be equal to negative 0.26. I expect that if I play this game long enough, I'll lose 26 cents on every time I play, right? And maybe I'll get really lucky and I'll win. That's my expected value. That takes care of this one. Now let's do craps. B, I have lose, win. I have my x. I have my p of x. And I have my x times p of x. If I bet $5 on the pass line in the dice game of craps, the probability of losing $5 is 251 over 495. This is negative 2. Let me Yeah, good. Negative 2.5335. I don't think I need that many numbers, but let's see. Now, the probability of making a net gain. So if I win, then I will win 5. And the odds of that are 244 over 495. So that becomes 5 times 244 divided by 495. And I get 2.4646 and so on. This kind of just keeps repeating. So now let's see what our net is, right? Or my expected value. So to find my expected value, I sum these. And I'll get my expected value. So I have 2.4, but I have that number minus 2.53535 equals, and that is negative 0.07. Okay, so that is my expected value if I play craps. And let's see, I bet $5 in the pass line. I don't really know craps, so I'm just going to have to read it. Probably losing $5 is this. So if we bet $5 on the pass line and win, we get our $5 back and we get an extra 5, which gives me $10. If we lose, obviously we lose all our money. The last thing it says is, which of the preceding two bets is better in the sense of producing higher expected value? But we have an expected value here of negative 0.26, negative 0.26, and we have negative 0.07. And we want to know which is bigger, because the bigger the expected value when I gamble, the better chance I have of winning. And if you look on a number line, here's 0, and here's negative 1, negative 0.5, negative 0.26 is here, and negative 0.07 is here. The more to the right it is, the bigger the number. What I want to do is play craps. The $5 bet in roulette results in an expected value of negative 26 cents, and the $5 bet in craps results in an expected value of negative 7 cents. Because you are better off losing 7 cents than losing 26 cents, the craps game is better in the long run, even though the roulette game provides an opportunity for a larger payoff when playing the game.